You ever see a drone just stop in midair? It's wild, right? It looks like it's totally defying gravity, like some kind of magic trick. Well, I'm here to tell you, it's not magic. And today, we're going to pull back the curtain and see exactly how it works.
I mean, think about it. An airplane has these huge wings, right? A helicopter has that massive rotor on top. But a drone, it's just this little machine with 4 tiny propellers. So what's the secret? How in the world does it generate enough power not just to lift off, but to dart around with such pinpoint accuracy? That's the big question.
And that's really the key here. It's not sorcery. It's just a super clever mix of physics and engineering. So let's get into it. Let's start with the absolute first problem you have to solve. How do you get this thing off the ground in the first place? Okay, so section 1, defying gravity. To get anything to fly, you've got to fight gravity. You've got to overcome its weight, that constant pull trying to keep it on the ground. For a drone, this whole battle comes down to one single, super important force. And that force is called thrust. The easiest way to think about it is that the propellers are basically really, really powerful little fans. They're spinning like crazy, grabbing huge amounts of air and just shooting it straight down. But wait a minute. If you're pushing air down, how does that make the drone go up? It seems a little backward, right?
Well, the secret sauce is all in the shape of the propeller blade. Take a look at it here. It's not just a flat piece of plastic. It's shaped like a tiny little airplane wing, what's called an airfoil. As that blade slices through the air, its curved top makes the air have to travel a longer, faster path than the air going underneath. This creates a pressure difference. You get low pressure on top and high pressure on the bottom. And what does that high pressure do? It pushes up. That's lift. And this is a textbook example of one of the most famous laws in all of physics, Newton's third law. You've heard it a million times. For every action, there's an equal and opposite reaction. The action here is the props shoving a whole bunch of air down. The reaction, the air shoves the drone right back, but up. The drone is literally climbing up a ladder of air that it's building for itself as it goes. How cool is that?
So really, flying just boils down to a simple tug of war. You've got gravity pulling the drone down, and you've got thrust pushing it up. When the upward thrust from those 4 propellers is stronger than the downward pull of gravity, the drone goes up. Simple. And when those two forces are perfectly, exactly balanced, that's when you get that magical-looking hover. All right, so we've solved problem number 1. We're off the ground. But now we have a whole new can of worms to deal with. You've got 4 motors spinning like crazy. What's to stop the body of the drone from just spinning out of control in the opposite direction?
Seriously, think about it for a second. If all 4 of those motors were spinning the same way, all that twisting force, that's called torque, it has to go somewhere. And where would it go? Right into the drone's body, turning it into a little quadcopter Beyblade. It would be totally, completely unflyable. But this solution to this is so simple, it's actually genius. Check out the diagram. Instead of spinning them all the same way, they spin 2 of them clockwise and the other 2 counterclockwise. So the twisting force from one pair is perfectly canceled out by the twisting force from the other pair. They just negate each other. And the result? No spin. Just a rock-solid, stable platform hanging in the air. Okay, so we've got a stable hover. That's awesome. But let's be real. A drone that only hovers isn't all that useful. The real fun, the real magic, is in the movement. So how do we take this perfectly balanced system and tell it to go somewhere and fast? It's actually pretty counterintuitive. You do it by unbalancing everything, but in a very, very controlled way. Every single movement a drone makes, every turn, every tilt, every forward sprints, it all happens because it's deliberately creating an imbalance between those 4 motors. The easy stuff is pretty straightforward. You want to go up? You speed up all 4 motors at the same time, more thrust. You want to come down? You slow them all down together. And to get that perfect hover, you just find that sweet spot where thrust and gravity are perfectly matched. But what about going forward? Okay, this is where it gets really smart. To make the drone move forward, that's called pitch, all you do is speed up the 2 motors in the back. That creates more lift in the rear, which naturally makes the drone tilt forward. Now think about it. The propellers are still pushing down, but since the drone is tilted, down is now also slightly backwards. So the reaction force pushes the drone up and forward. The more you tilt it, the faster you go. And moving side to side, which we call roll, works the exact same way. Want to zip off to the right? Just tell the 2 motors on the left to spin a little faster. The drone tilts to the right and bingo, that redirected thrust pushes it sideways. So let's recap real quick. To go forward, the back props speed up. To roll right, the left props speed up. And what about turning in place? That's called yaw. For that, you mess with that perfect torque balance we set up earlier. You speed up the two props spinning clockwise and slow down the two spinning counterclockwise. This creates an intentional, controlled spin, letting the drone pivot perfectly on the spot. Now, I know what you're thinking. This sounds insanely complicated. There's no way a human pilot could make all those tiny constant adjustments fast enough to keep this thing from just flipping over. And you're right, we can't. That's why there's one last absolutely critical piece to this puzzle, the drone's brain. And that brain is called the flight controller. It's basically a tiny computer that acts as the drone's central nervous system. It's doing a million things at once. It's listening to what you're telling it to do with the controller, it's constantly reading data from its sensors, and it's performing thousands of calculations every single second just to tell each motor exactly how fast it needs to spin at that exact microsecond.
And this is what one looks like. These little boards are just amazing pieces of technology, super powerful microcomputers that have one job and one job only: keeping the drone flying perfectly. The fact that these have gotten so small, so fast, and so powerful is the #1 reason why modern drones are so incredibly stable and, frankly, so easy to fly.
So how does this little brain know what's happening in the real world? It has senses, just like we do. It has tiny little sensors on board. A gyroscope feels any kind of tilt or rotation, and an accelerometer feels any change in speed. Together, they're constantly feeding data to the flight controller, telling it, hey, a gust of wind just pushed us, or whoa, we're starting to drift, and the controller can react instantly to fix it. So, when you put it all together, it's pretty clear, right? It's not magic, it's just this beautiful, elegant dance of science. And by mastering these principles, we've unlocked a ton of incredible, real-world uses for this technology. I mean, you see them everywhere now. They're used for those jaw-dropping movie shots, for search and rescue missions in places people can't easily go, for delivering emergency supplies, even for checking on farms to see how crops are doing. This tech is really changing the game in so many fields. And it all boils down to a few key things. You've got physics, with Newton's third law letting propellers create thrust. You've got aerodynamics in the shape of the blades, and you've got computer science with that tiny flight controller acting as the conductor for the whole orchestra, running complex algorithms and making thousands of adjustments every second. It's a perfect symphony of science and engineering. So, at the end of the day, we've basically figured it out. We cracked the code. We took the laws of physics, added a whole lot of computing power, and taught these little machines how to fly with incredible grace and precision. Which, of course, leaves us with one really exciting question to think about. Now that we've taught them how to fly, what are we going to teach them to do next?